A very warm welcome to the 8th lecture on the subject of wavelets and multirate digital signal processing. In this lecture, we shall build more intimately the connection between the filter banks that we talked about in the previous lecture and the underlying continuous time functions, the scaling function phi t and the wavelet psi t. We suspect all the while that this connection exists. After all, we built the filter banks out of the idea of multi-resolution analysis with the Haar multi-resolution analysis as an example. Before we go further, we must now make a few generalizations, which will help us then to build that connection more intimately. So, let me quickly put down what we intend to do in today's lecture. We intend today to relate the scaling function phi, the wavelet psi and the filters that we talked about in the filter banks, namely the analysis and the synthesis filter banks. Towards that objective, the first step is putting down a generic structure for the analysis and the synthesis filter banks. So, you see, let us consider the generic structure for the analysis filter bank first. Incidentally, we should be talking about a 2-band filter bank here, and that is because we are talking about dyadic MRAs here. Recall that dyadic refers to powers of 2 changes. So, what we are talking about is the generic structure first of a 2-band filter bank, 2-band analysis filter bank. Now, I will start from the Haar. In the Haar, it looked like this, Haar MRA I mean, it looked like this, recall. This was the structure, and we also analyzed the frequency domain behavior of these 2 filters. In fact, this turned out to be a crude low pass filter, and this turned out to be a crude high pass filter. Of course, high pass and low pass as understood in the discrete time sense. Now, we also recall 2 other properties of these 2 filters that we had brought out the last time. One was what we call magnitude complementarity. Magnitude complementarity in the sense, if we simply summed the filter system functions together, you got the identity system function 1. The second was what was called power complementarity. So, if you sum the magnitude square, you got a constant independent of omega, I mean, which means if you took a sine wave and looked at the power of the sine wave emerging from each of the two branches, those powers would add up in a complementary way for each frequency. Magnitude complementarity, power complementarity. Now, if we looked at the Haar case, it was not very clear which idealization we were moving towards, but then we had put down the idealization the last time. So, let us now put down the complete idealization. We have a crude low pass filter there. What would be the refined low pass filter towards which we are moving in this analysis filter bank? Now, when we say towards which we are moving, what do we mean? Why should we move? Why can't we be content with the Haar multi-resolution analysis? That is also a question that we need to answer. We will have to take the answers to these questions one by one. So, let us first answer the question, what is the idealization towards which I am trying to move? So, let me put down first the actual frequency responses once again, and then the ideal frequency responses towards which we are trying to move. So, the actual Haar analysis filter responses the 1 plus Z inverse by 2 filter had a response that looks like this, essentially mod cos omega by 2 between 0 and pi. Of course, recall that there is periodicity, and the 1 minus Z inverse by 2 filter had essentially a response that looked like mod sin omega by 2. And you will recall that there was magnitude and power complementarity here. In fact, cos squared plus sin squared is 1, and therefore, there is power complementarity. And if you just add up these system functions together, 1 plus Z inverse by 2 plus 1 minus Z inverse by 2, you get 1, and that is magnitude complementarity. Now, if you look at these two responses and if you mark them around the center, the center is pi by 2. So, if you mark them around the center, you see a certain symmetry in these responses about the center. That gives us a hint where we are moving towards in the ideal sense. Ideally, we are trying to make this a low pass filter with pi by 2 as the cutoff, and again we are trying to make this a high pass filter again with pi by 2 as the cutoff. So, let us put down the ideal analysis filter responses towards which we intend to move. So, the low pass filter should have a response that looks like this between 0 and pi. it must be 1 between 0 and pi by 2 and 0 between pi by 2 and pi, and this entire pattern must be mirrored between minus pi and 0, and of course, then repeated the whole pattern between minus pi and pi, then repeated at every multiple of 2 pi. All this is of course naturally from the properties of a discrete time Fourier transform or a discrete frequency response. So, I am just showing the region between 0 and pi and what happens between minus pi and 0, and then at around every multiple of 2 pi follows naturally. So, this is the low pass filter response. Similarly, the high pass filter response, which I will draw here. The high pass filter needs to have a response of 1 between pi by 2 and pi, and of course, whatever is between 0 and pi is mirrored between minus pi and 0. The response is 0 between 0 and pi by 2, and then of course, periodically repeated at every multiple of 2 pi. Let us call this LPF ideal. So, LPF ideal and high pass filter HPF ideal. So, these are the frequency responses of the analysis filters towards which we desire to move. Let us now put down the ideal frequency responses of all the filters, analysis and synthesis, in a 2 band filter bank. So, where are we moving? In what direction are we moving? So, the ideal two band filter bank would have the following structure. The input sequence here being fed to LPF ideal here, HPF ideal there, downsampled by 2 subsequently, this is the analysis portion, followed by upsampled by 2, again low pass filter ideal here, high pass filter ideal here, and the outputs from this are to be added to produce the overall output. So, here I have just marked the outputs to fit into the drawing. The output from this and the output from this are added together and produce the overall output. This is the ideal 2 band filter bank. Notice in the ideal 2 band filter bank, the analysis filters and synthesis filters are identical. There is no difference. In fact, on one of the branches, both of them are ideal low pass filters with a cutoff of pi by 2. On the second branch, both of them are ideal high pass filters, discrete time filters with a cutoff pi by 2 once again. So, you see complementarity there in some sense, and in fact, if you look at it, these are obviously magnitude and power complementary. If you take the frequency responses and add them together, they of course add up to a constant. If you take the square of the frequency responses and add up the squares, they again add up to a constant, trivially, because there is no region of overlap. That is simple. So, in fact, that is where we are moving towards. Now, it is a moot point so far, as I said, why we need to move any farther from where we are. Why do we need to work harder than what we do for the Haar wavelet? Are we lacking something in the Haar wavelet? Well, of course, one thing that you can see we are lacking is the distance from the ideal filter. We are far from the ideal. If we look at the two frequency responses of the Haar's analysis side and therefore, also the synthesis side, I had left it as an exercise to calculate the frequency responses for the synthesis side. They are almost the same. We are very far from the ideal. So, that is of course clear. But why we need to move farther from the Haar can be answered in many ways. We shall take up this answer slowly, part by part. But before we take up that answer, what we need to do is now to go the other way. We came from continuous time to discrete time. Now, slowly we want to see if my design of a multi-resolution analysis relates to the design of the two band filter bank that I have just drawn here. So, you see, we have ideal filters here and we have written down the frequency responses of the ideal filters. But in practice, the ideal filter can never be attained.